Okay. Have you come back? The one who go to Tapao? Okay. Wow, so fast. Okay, okay. So what time you want to end? Should be by right. Should be we have another 2 hour, but up to you lah. If you want, maybe like 3 o'clock, we will end the class 3 o'clock. Is it okay? Let me see. This tutorial questions done. Done. Okay, this one done already. The first one. Okay lah. I try to be quick lah. If I can finish the syllabus earlier, then we can end the class earlier lah. So I still know yet know when we're going to end lah. Okay, I try to be quick. Okay, so differentiation. Differentiation. When we talk about the differentiation, okay, this is differentiation of the complex variable. It's not the same as before. Before is normal differentiation. This one is with complex. Okay, that means with imaginary number. Okay, when we talk about the differentiation, we must talk about the first principle, because first principle is the first thing. Okay, first we learn when differentiation developed, the first thing is come from the first principle. So first principle, no matter is from what, okay, from which area, differentiation of normal number or differentiation of the complex is the same. Is this one, okay? Limit when your delta z is very near to 0, okay, and then fz plus delta z minus the fz, and then divide by the delta z. If this one exists, and then that means we set this one, we have the differentiation first derivative, okay, we have the first derivative, and it's f delta z, f prime z, okay. I repeat again. If this one exists, then we said it is differentiable. Okay, it is differentiable at what point? At the point of z. I don't know what is this, but if you are given one point, then and this one is axis, then we said this one is differentiable at the point of z. Okay, this is just a definition. Okay, and then we said the complex function is analytic, regular, or holomorphic at the point z equal to z naught if it is differentiable. Okay, and around the neighborhood. So that means you have one point, and then around that point is differentiable. Then we said it is analytic, regular, holomorphic. Holomorphic quite seldom will be used lah. Okay, analytic quite normal. We use analytic. Regular sometimes, but not so much. Okay, so a complex function f is said to be analytic on an open set if f is differentiable. Okay, that means inside this set is differentiable. Okay, then we said this set is analytic. A complex function is set to be analytic on this open set. Okay, and then if your S equal to C, that means your whole set is equal to your whole complex function, then we say it is entire. Okay, entire. That means your set, that means this function is differentiable at whole complex. No matter where is your plane, as long as this is your z plane, the function can be differentiable everywhere. Every complex. Okay, then we say it is entire. Okay, so now we have a look. If you want to differentiate this one, okay, just very simple lah. You just take down n and then z and then n minus 1. This is normal differentiation, normal differentiation lah. Okay, but if you want to use first principle, okay, first principle, that means you have this you have to use this formula. So this formula fz plus delta z minus fz. So since this is your fz, so you change this one become z plus delta z power of n, and then minus the zn. Okay, divide by delta z itself. Okay, and then this one I can expand it by using the binomial expansion. Okay, and then minus the zn. So zn and zn cancel each other. So you will left only this part. And when your delta z is near to 0, so this one near to 0, near to 0, near to 0. Okay, so what you left there? Not yet lah. Okay, because if you direct put like that, this one also near to 0. So you will have something 0 divided by 0. As I said, I think I told you before, is it? 0 divided by 0 should be indefinite. Okay, 0 divided by 0 is indefinite. I can have 0 divided by 1. I can have 1 divided by 0. This one, I will have 0. This one, I will have infinity. But I don't have 0 divided by 0. Okay, I also can have 1 divided by 1. 1 divided by 1 is 1. Okay, but I cannot have 0 divided by 0. You cannot say, oh, 0 divided by 0 is 1 because 1 divided by 1 is 1 ma. Or 1 by anything divided by 0 is infinity, so this one should be infinite. No. Okay, and you can also say 0 divided by anything is 0. Okay, so you said this one is 0. No, no such thing. 0 divided by 0 should be indefinite. Okay, that means no defined, undefined. Okay, this is an undefined number. Okay, undefined number, so we cannot direct put inside. Okay, so what they do here is they separate them. Everything divided by delta z, delta z, delta z, then they have this one. Then now only they put in delta z equal to 0, this one equal to 0, this one equal to 0, then left only this part, which is nz, n minus 1. Sorry, 1 minute. Okay, sorry. Oh, so we continue. Okay, this is by first principle. Okay, and also this one you can have a look lah. Normally lah, I won't ask the first principle in your final exam lah. Those tests I know you decide lah. Okay, but you still have to know what is first principle lah. First principle actually just normal lah. You just put in the function, okay, fz plus delta z, and then the formula is always this one, and then change this one into z plus delta z, and then try to merge them. Okay, merge this one. Merge this one together, then you will have here, okay, and then solve it, you will have here, okay, and then what you do, this one and this one can cancel each other, so you left this part only. So left this part, then now you can put in your delta z. You always can try, I think you learn limit before, okay, we always try to put the delta z inside the limit. If you doesn't get 0 divided by 0, you doesn't get infinity divided by infinity, then you may proceed. Okay, you may direct jump into the conclusion already. You may direct put into the 0 into the function and then get the answer. Okay, but not always. Sometimes, okay, for example, this one, if you put in 0 direct here, 0 direct here, not necessary to get out of these two. So that means you will get something undefined. Undefined then cannot. Okay, then you have to manipulate a bit. Okay, so hence I get the answer of this one. Okay, so what we see here, this one is defined everywhere except when your z is 0. So this is not entire. Okay, this one is not entire because z equal to 0 is undefined, is infinity. Okay, so that's why this one is not entire. So it's analytic any point except z equal to 0. Like just now, this one, no matter what is your z, okay, as long as you put inside that, then you can get a particular answer, okay, get a particular value. Hence, we said Zn is entire for this case, okay. That means it's analytic everywhere lah. Okay, so this case, Fz equal to Z conjugate, okay, or Z bar, okay. So this one, if you try, you put inside, you have this one, and then we try to break it. We try to break this one into Z bar plus delta Z bar, okay? And then we try to this one and this one cancel each other, so I will have this one, okay? You will have this one, and then that means, okay, you will have here. You have here, so it can be positive one, it can be negative one, depend on what is your delta z, okay? What is your delta z? So it can be negative one, it can be positive one. If your delta y is going to 0, if your delta x is going to 0, then you will have positive one. So that means you will have different point. When you have two different point, then we said this limit is not exist. Limit is not exist, then it's not differentiable. Totally not analytic, totally not differentiable. Okay, so not differentiable, then we don't need to talk about the analytic lah. Okay, so this is a differentiation lah. Differentiation just normal lah. Differentiation of Zn, we have this one. Sin Z become cos Z. Sin hyperbolic become cos hyperbolic. Ln become 1 over Z. And then Ez still is Z. Cos Z is negative sin Z. Cos hyperbolic Z will be sin hyperbolic Z. Okay, this is just like normal lah. Okay, normal what we have in the normal in algebra lah. Okay, and then we also have the rules. Okay, just like normal, we have the rules. For example, we have linearity property. We can take out the a, and then we can take out the b, become this one. Okay, just like if you differentiate 3x squared plus 5x, it can also be, if you want to differentiate this one, then it also can be 3 and then differentiate of x squared, and then plus 5, and then differentiate of x. It's the same thing, but change the x into the z. So this rule is still applicable in the complex number. Product rule also the same. If you have 2, okay, you have uv, then you'll be u dv dx plus v du dx, okay? And then quotient rule, when you divide, then you have this one. It's the same thing. It's still the same thing, okay? And then the chain rule. Chain rule is still also the same, okay? In the function, you have the function. Okay, so it is like, for example, how to say that? We will just have a look at this one. If you want to differentiate this one, okay, normally what we do, we use substitution, is it? We use, okay, I want to differentiate this one. I want to differentiate this one. I let, sorry, I type cable. 1 minute. Okay, so we continue. Okay, the chain rule. Chain rule, normally what we do is we let u equal to z squared. Okay, because now, and then we let v equal to sine hyperbolic u. So if I want to find the differentiation of this one, that means I want to find the dv dz. And I can break the dv dz into the dv v to u times u to z. so that if you cancel each other, you still have dv dz. So what you need to do is you just differentiate the dv du. dv du, differentiate sine u become cos u, cos hyperbolic u. And then du dz become 2z. And you have to break your u into the z square as well. So you will have 2z cos hyperbolic z square. So this one will be the answer. I think you met this one before, is it? Chen rule. Have a look. Try to refresh a bit. Okay, so we continue. Next theorem. Okay, Cauchy-Riemann equations. Okay, they said if a complex function, okay, this is a complex function, and then your z is x plus iy. Okay, your z is x plus iy, your w is u plus iv lah. Is analytic. Let's say this is analytic. That means it's differentiable. It's differentiable lah. Okay, then the real function u equal to uxy and v equal to vxy. That means this one. Okay, must satisfy the Cauchy-Riemann equation. Okay, that means ux equal to vy, vx equal to negative uy. I repeat again. What is mean by this one? They said you want to check this function is analytic or not. Very simple. Okay, if this function is analytic, that means your ux must be equal to vy, your vx must be equal to negative uy. If fulfill this one, okay, if fulfill this one, then it is analytic. And your differentiation will be ux plus ivx. Okay, now we have a look. This one proving I don't want to touch lah. If you want, you can have a look lah, but I don't want to touch the proving. Okay, the converse of this theorem is not true. Okay, you have to take note. They said this one is analytic, then fulfill this one. Doesn't mean that if the function fulfill this one, then must be analytic. Not necessary. I repeat, if fulfill this one, not necessarily must be analytic. Can be not analytic as well. Okay, and then if the real function u and v does not satisfy the Cauchy-Riemann equation, then the complex fz equal to u plus iv is not analytic. Okay, what they said here, if this one is analytic, then must fulfill this one. If not fulfill this one, then it's not analytic. Okay, that's all. They does not say if you have this one, then it must be analytic. No, they only said if it is analytic. They said if A, then B. Okay, you also can make it as if not B, then it's not A. But you cannot say if B, then A. It's different. Okay. So I continue again. Okay, so next theorem. A complex function u plus iv is analytic. That means, okay, if and only if u and v satisfy the following two conditions. Okay, satisfy the Cauchy-Riemann equations, which is this one. which is this one, and u and v and their first partial derivative are continuous. That means the first differentiation, okay, your ux, vx, uy, vy is continuous. Then we said it is analytic. These two theorems are different. We have a look again. Like just now what I said. Only this part is not enough to say this function is analytic. You have to add another function, another condition, which your ux, vx, uy, vy are continuous. Then we said this function is analytic. You have to add these two conditions. Only you can say it is analytic. So this is another theorem. Okay, that's how the theorem said if analytic, then must fulfill the first one, but does not mention the second one. Okay, if fulfill this both of them, then it's analytic. You can make it inversely. Okay, if and only if. Okay, so now you try to have a look on the example first. First example. Later I will explain it. Okay, so now look. I want to prove that z squared is entire. So what I mean by z squared that means is okay, your z is x plus iy. So you expand it, you have x squared minus y squared plus 2ixy. Okay, you expand the x plus iy lah. So now, in order to prove it is analytic, okay, to prove it is entire, okay, entire. So okay, we try to do the Cauchy-Riemann. Cauchy-Riemann, that means we try to differentiate this one by okay, now your real part will be x squared minus y squared. Your v, your imaginary part will be 2xy. So your your ux. So from there we know the ux is 2x. 2x is a straight line, it's continuous every way. Okay, and then your uy is negative 2y, it's also a straight line, continuous every way. Okay, and then your vx will be 2y, is the same thing. And then your vy is 2x. So what you see, okay, Cauchy-Riemann is what? Cauchy-Riemann is ux, vy, vx, negative uy. So ux, vy is the same, vx is negative uy. So this one fulfills the Cauchy-Riemann equation, and it is continuous. So hence we know that this one is analytic everywhere. Okay, analytic everywhere. Hence we know this one. Okay, fulfill the Cauchy-Riemann, and then are continuous. So since I know it's continuous everywhere, it's fulfill the Cauchy-Riemann. So I know it's continuous everywhere. Okay, it's differentiable everywhere, is analytic everywhere. Hence, I know this is an entire. Okay, and then what is the first derivative? First derivative according to this one will be ux plus ivx. So it will be 2x plus I 2y. So this one will be the first derivative. Okay, if you take out the 2, then you will have 2z. Okay, because it's x plus iy. So that means we know that, okay, z squared differentiate is 2z. Just that simple. Okay, so next one is I want to prove that this one is not analytic. Okay, this one is not analytic. Analytic, that means it's not fulfilled this condition. Okay, so now we'll try to have a look. I have z bar. Z bar, that means now will be x minus iy, because I assume that my z is x plus iy. So my z bar will be x minus iy. So now my u is x, my v is y. Sorry, negative y. So I differentiate the ux is equal to 1, but I differentiate the vy, I get negative 1. These two are not equal. Not equal, that means it's not fulfilled the Cauchy-Riemann. Not fulfilled the Cauchy-Riemann, then hence it is not analytic. Okay, so third one, I want to prove that this one is not analytic as well. Okay, we try to prove. Okay, so modulus of z and then square. So that means I want to find the magnitude. Sorry, 1 minute. Okay, I want to prove this one is not analytic. So modulus of what? Modulus of, sorry, if I have my z is x plus iy, then my modulus z will be x squared plus y squared. So x squared plus y squared. So that means square of this one, then will be holding square lah. Square, that means this one will be cancelled lah. Okay, so I left only x squared plus y squared. So this one only real number. Real number, that means you only have the u, but you don't have the v. So if you differentiate this one, you will get 2x. Okay, but if you differentiate this one with respect to x, you will have 2x. But if you differentiate this one, you will get 0. Alamak. Okay, you will only get 0. Okay, so actually this one should be not equal lah. Ux not equal to Vy, except what? Except when your x is 0. So only when the point is 0, 0, then it is differentiable. If it is not 0, 0, then it's not differentiable. So that's why we said, okay, this one is not analytic because they are not the same. Okay, have a look again and please ask if you have any questions. Okay, so here, because here fz equal to z square only fulfill these two when it is 0, 0. So we said it is only differentiable at z equal to 0. Okay, other place not differentiable. Okay, only one point are differentiable. Okay, okay, so this one, a shortcut rule for analytic function. Okay, so because in order to check whether it is analytic or not, we need to use, if you apply this theorem, you need to check whether it is fulfill the Cauchy lemma or not, and then whether their first derivative is continuous or not. Okay, so this one, they have another shortcut. Okay, if a complex function fz equal to u plus, okay, is analytic, then both fz and f prime z can be expressed in terms of z equal to x plus iy by formally setting y equal to 0, replacing x with z. Okay, apa dia cakap? Okay, what is talking about this one? Okay, what this talking? What this about? What this text is talking? Okay, so they said you can express this one in terms of z equal to x plus iy. Okay, where you set the y is 0 and then replace the x with z. Okay, now we try to have a look what they said there. Okay, this example, fz equal to 1 minus 2xy plus ix squared minus y squared is entire. Okay, I want to show this is entire. So how to show this one is entire by using the shortcut here. Okay, so now what they talking here, so I know my fz is 1 minus 2xy plus ix squared minus y squared. If you compare, this one is u, this one is v. So again, by Cauchy-Riemann, okay, we try to differentiate this one, okay, by this one by x, and then this one by y, see whether they are the same or not, and then this one by y, this one by x, see whether the negative of it is the same or not. So if they are the same, then we know that it's fulfilled the Cauchy-Riemann. Okay, and then I also know that negative 2y and 2x is continuous everywhere. So I know this is entire. Okay, this is by using the Cauchy-Riemann theorem. Okay, so now we try to see, this is normally what we do. This is normally what we do if we want to check whether it is analytic or not. Okay, so now another way. Oh, sorry, not another way. Okay, if it is analytic, then you can set fz and f prime z can be expressed in terms of this one. So now let's see what they said. Okay, we try to set y equal to 0 and then replace x with z. Okay, so that means I have this one. My y is 0, so this one will be gone. And then I try to replace this one as z. So that means my fz is, okay, my fz only left 1 plus ix squared. This one will be 0 lah. Okay, plus iz squared. So this one will be my fz. And then what is my f prime z? Okay, my f prime z will be ux plus ivx. So what is your ux? That's all. Negative 2y. Ivx 2x. So negative 2y. So this one, okay, this one will be f prime z. But don't forget, you have to replace your y as 0, your x as z. So now your f prime z will be 2iz. This one is only when this is analytic. Okay, this is analytic, then you can direct jump to the conclusion. Your fz will be this one, your f prime z will be this one. You try to have a look again. Okay. I want to show that 1 minute. Let me see this one until where. Okay. Okay, so we try to have a look this one. So first, I want to prove this one is analytic everywhere or is entire. Okay, this one I leave it to you lah. You just compare to u, v, and then you differentiate u, differentiate v, differentiate your u with respect to x, differentiate with respect to y, and then also your v also to xy. Hence, you will know that they are fulfilled the Riemann. Okay, now I want to find the fz and f prime z. So if this one is entire, then only I can do so. So what will be your fz? Your fz will be substitute your y as 0. Cos 0 give you 1. So you left only sine hyperbolic 2 x, don't put x, put z. Okay, and then y becomes 0, sine 0 is 0. So this one will be your fz. And then what will be your f prime z? F prime z will be ux plus ivx. So it will be this one plus I of this one. Okay, so that means will be 2 cos, again don't put x, put z, so 2z, and then cos 2 times 0, so cos 0 is 1, so no need to put inside, and then plus I times this one. Okay, I times this one, but put your y equal to 0, sine 0 will give you 0, so whole thing will be 0, so no more there. So your fz will be this one, your f prime z will be this one. Okay, which they ask you to find the fz and f prime z. This one is only when it is entire you can do so. Okay, hence I get the answer of fz and then I get the answer of f prime z. Okay, have a look and please ask if you have any questions. Okay, so I continue again. Zeros and singularity of a complex plane, a complex function. Okay, so what is zero? What is singularity? So now we have a look. Okay, z naught, we set a point is z naught is a 0. Okay, if f is analytic at z naught, okay, is analytic on this point, and then f z naught is equal to f prime z is equal to f prime z up to your m lah. But when this one is order of m lah, okay, but when it is f differential of m times, then it will become 0. Differential 1 time, 2 time, 3 time until m minus 1 time is still same as your f z naught. But when you differentiate until m times, it is equal to 0. Then this one is called z naught is 0 of order m. Okay, z naught is order 0 of order m. Okay, and then if 0 of order and 1 and 2 is 1 is called simple order, simple zeros. 2 order of 2 means it's double zeros. Okay, that means what is simple? Simple means that is analytic at z naught, and then f z naught equal to 0, and then your f prime z naught is not equal to 0. I repeat, if simple, that means when you put inside your z naught, you will get equal to 0. But when you differentiate it, it won't be 0. Then we call simple 0. If double 0, f z naught and f prime z naught is still 0, but f prime z naught will be not equal to 0. Okay, so now we have a look. This example, let's say I have this example. Okay, so I try to solve the fz equal to 0 because I want to find where is the zeros. Okay, I want to find the zeros. So I try to put the fz equal to 0. So fz equal to 0, then only two answers. Either your z is 1 or your z is I. So you have 1 and I are 0 of f. Okay, so I know this is 0. Okay, but I still don't know this is of order how many. Okay, so now we try. Can be simple. Okay, can be simple, can be double, or so on. Okay, so now what we do, we try to differentiate. Differentiate, I have this one. So now what I do is I put inside I, see whether it is 0 or not. Okay, put inside I get not equal to 0. That means I know that fi is 0, but f prime I is not equal to 0. Then you stop here. Then because based on this one, I know this is a simple 0. Simple 0 because first order is already not 0. So I know this is simple 0. Now I try f, I know f1 is 0. And then I try f prime 1 is still 0. Okay, I put inside this one, I still get 0. And then we try again f prime 1. F prime 1, I get something not equal to 0. Then by using this one, I know this one should be first order, second order, third order already. First order, sorry, double. Okay, first order, second order. So this is order of 2, which is double 0. Okay, any questions? Okay, so I continue again. Okay, so they said there are another theorem set. Okay, f has a 0 of order m and z naught if fz is equal to z minus z naught m times a gz. If you can, okay, write into this way. Okay, if you can write into this way, and g is analytic lah, the g must be analytic at z naught. That means at this point. Okay, and gz naught itself is not equal to 0. Then we said f have a 0 of order m. Okay, now we have a look. We try to have a look. What is mean by this one? So actually, we don't need to try for so many times. We don't need to try for so many times. Sometimes we don't need to try for so many times in order to check this is in order of what. Okay, so now we have a look. Determine the location and order of 0 of each of the functions. Okay, so I have this one. So from here, what I can know, I have z equal to, because if this one you make equal to 0, that means this one equal to 0, this one equal to 0, this one equal to 0. So z equal to negative I, and then 1 over 2, and then negative 4. Okay, so they said if you can make it as power of m and then times gz, so that means I take out this one. When I take out this one, I left only this part. Okay, so this one is a first order. So because it's power of one, that means it's order of m. So that means this is a simple zero. For z equal to half, that means you take out this one, then what you left is only this part. Okay, so this is a double zero. If this one -4, it will be -4 because it's power of 5, so it will be order of 5. So just that simple. So that you don't need to differentiate. Okay, you don't need to. If you differentiate, then it will be very long story. Okay, you see here you have to differentiate f prime prime z. You have to differentiate f prime z, and then you have to try to put plug inside and then see whether what is your answer and so on. So you will see this one is very difficult. Okay, this one is a very long story in order to determine what is the order. But if you use this way, okay, if you use this way, you direct get what is the zeros. Okay, this one zero is -4, and then 1/2 -I. Then direct you get the zeros, and then from here you can know the order directly. Then no need to do so many things there. Okay, it's much more easier. Okay, so we continue. Okay, we continue. Tangent z. Tangent z is what? Is sine z over cos z. So that means I can make it into, okay, 1 over cos z. Sorry. I can make it into sine z times 1 over cos z. Okay, so from here, if I want to put this one equal to 0, okay, this one equal to 0, that means your z will be n pi. Your z will be n pi. So because it's power of 1, so I know that this is a simple 0. Okay, if you try to differentiate, you will know that it's not equal to 0 anymore. But because this one is power of 1, power of 1, that means automatically I know this one is a simple 0. Okay, that's that simple. Okay, so singularity. Okay, so let's say I have the definition. This is a definition of singularity. Okay, function h and g are analytic at z0. Okay, and then h z0 is not equal to 0, g z0 is not equal to 0. Okay, and then the function is defined by h divided by g. Then we said z0 is singular point or pole. Okay, of the function f. I repeat again. This one, okay, z0, if you have this function, if you have this function, and then when you put z0 into the h, it's not equal to 0, but when you put into the g, it's equal to 0. Okay, and then these two must be analytic on the z0. Then z0 is called pole or singular point of the function f. Okay, so moreover, if your z0 is a 0 of order m and g, where m is finite. Okay, so that means your z naught okay, is order 0 of order m of g only, only g, is only g. Okay, and then your m is finite, then we said z naught is a pole of order m or singular point of order m. Okay, so now we have a look. You try to have a look for the first example first. Okay. So one minute, yeah. Sorry, wait me a while. I have something. Okay, you try to do a tutorial first. Tutorial 2. So sorry because I have something. You can try to do the question 1. Maybe later we can discuss 1A. B, I don't want to do. Question 2, maybe A, B, C. Okay, D and E, I left it to you. I begin 1A, A, B, C. Okay, and then question 3, try to do. Question 4 also you can do. Okay, try to do the tutorial 2 first. Okay, 1A, 2 ABC, question 3, question 4. Okay, sorry, I have something.